Hello, this is the second video of week number 1 of COMP442 and 6421. This is compiler design. Here we're gonna go over the entire somehow compilation process or different aspects of compilation and interpretation and things like this. Basically, it's going to be just very briefly going over the steps involved and the different variants you may have in translating a computer program into an executable. I'm not claiming here that I'm going to be going into all the details, just basically going to skim over the important concepts which are intersecting somehow with what we're doing in the course. So what is compilation? So essentially, what is a compiler? A compiler is a translation system. So it is essentially translating a language into another language, because you want to be able to execute your programs onto a computer. The computer does not know the language. For example, the computer does not know Java, it does not know C++, whatever language you're using. Computer does not know this language. So you need to have to build a computer program whose goal is to translate this language into the only language that your computer will understand, which is the binary language. When you load your executable onto the computer's memory and execute it, it needs to be stored in binary inside of the computer's memory so it can be executed. That's the only language that your computer understands. So if you write a program, for example, in Java, you need to somehow translate it into binary somehow so that it can be executed by the computer. So essentially, when you compile a program, you're translating a program into another program. Translating your Java program, which is easy for you as a human to understand, into the binary program that is the only language that the computer will understand or be able to execute. So what is the source? Because there is a terminology. I'm going to use some terminology here in this this first introduction. It's important to use the right terms as always. So I'm going to define some of these terms, not necessarily define, but use some of these terms. For example, when you have a compiler, it basically compiles code. In this case, it's the source code. And then it generates another code, which is called the target code. So source and target are two terms related to compiler design. And you have the source language and the target language. In many cases, as I exemplified before, target language would be the binary language that is understandable by the computer on which you want to execute the program. Of course, the target language can be a different language. For example, if you compile your Java program, as we will see later, when you want to execute your Java program, you first have to compile the Java code into bytecode. So in this case, the Java compiler is a translator that translates your Java program into a bytecode program. The bytecode program is not a binary program. It is a program that is somehow written in a special language, an intermediate language that is called the bytecode, which is your target language in this case. Then in the case of Java, then you can use an interpreter to execute the bytecode. We'll come back to that later. All this to say that a compiler translates from a source language to a target language. These, depending on what your compiler is doing, what's the purpose of this compiler, it may have different source and different targets. But the objective is always to translate a program into another program. So what's this translation in a very abstract way to describe it? What is this translation business doing? When you want to translate something, if, for example, I'm speaking English here and then you want to translate what I'm saying into French, the first step is you have to understand what I am saying. What's the meaning of what I'm saying? Then you actually translate this meaning into another language. Okay, so those two steps, two essential steps here. First, understand what I'm saying, then figure out what's the meaning of what I'm saying, and then translate this meaning into another language. Okay, so there are steps involved here. The same thing goes for a compiler. So you need to first understand, well, first of all, figure out if this program is a valid program, because, for example, I might be pretending to speak English, and then my sentences might be all mangled and they don't make sense. So that would be me speaking English for which there cannot be a meaning to my sentences, in which case you would not be able to translate or convey the lack of meaning of what I'm saying, essentially. Okay. So yeah, so you're translating a source language into a target language. First is you need to understand, figure out if this program or what you're translating is proper and can have a meaning. If it has a meaning or can have a meaning, then you can actually translate it. So that's one of the things that the compiler does. In fact, a very important aspect of what a compiler does is to figure out the potential mistakes that there are in the program. If a compiler is to be useful, not only should translate the programs, but if there are some, for example, grammatical mistakes in the program or semantic mistakes, it should inform the programmer so that programmer knows how to fix the errors that there might be in their program. So as I hinted at before, so the only language that your compiler will understand is binary. So essentially in the computer's memory, there's a sequence of words, and words is a certain a series of a binary zeros or one of a certain length, and then each of these words are stored consecutively in the computer's memory. Some of these words might be instructions. Some of these words might be data that are manipulated by the instructions. So if they are instructions, then they have to be in a certain predefined format that is predefined by the architecture of the computer on which you're executing this, this code, this stored in the computer's memory. For example, you might have this word here that in which these first the first element of the actual word might be the name, the nature of the operation. For example, here that we might say this means addition operation. Then you might say there is these following bits here, which represents the first operand. This is the second operand. This is the third operand. In this case here, it's assumed that this means add the value of register number 1 with the value of register number 3, and then put the resulting value in register number 15. Okay. So this is basically what the computer would understand. So the series of zeros and ones, this is a word which has a certain meaning, and that's things that the very essential low-level words that a computer will understand, or commands that the computer will understand. Of course, you could write your own program in binary. That's what used to be done in the very early days of computers. People will write their programs in the binary language. Of course, you should understand that there's very quickly a limit to the size and complexity of a program that you can write in binary before, as a human, you just get lost in this this sea of zeros and ones. So having a language that is such low level, this is not how our brain thinks. Somehow this is how the computer thinks. This is not how a human thinks. So it's for a human to be able to express more elaborated concepts, they need a more elaborated language. So one of the first languages that were ever designed were assembly languages. Essentially here, the assembly language, what it does is basically it puts mnemonics that are more easy to understand or remember by a human. So you might say, for example, this series of zeros and one we saw before, we might say, this represents add R1, R3, R15. This is much more easy to see and use by a human. So assembly language, even though it's still very low level, it's much more usable by a human, and it kind of multiplies by a certain number of level of magnitude, the size of program that a human can design before, before it again becomes too low level to be able to enable a human to design a program of a certain magnitude. Okay, and that's actually what happened, and that's why people had to design even higher level of abstraction to enable the design of more complex programs. Essentially, programming language design or the emergence of newer programming languages in a history of programming languages had to do with productivity. If you're using a lower language, lower abstraction level language, there comes a point where, yes, you can write programs, for example, in binary, but after a certain point, there comes a point where the time you spend actually writing the program becomes more than the actual time you save by actually using this program. Okay. So after a certain level of complexity of program, it becomes very hard to add more lines of code to a program if you're using a lower level abstraction level as in your language. That's why people design more abstract languages that were able to uh, uh, express real life concepts. You can express real life concepts in binary language, but it requires a lot of gymnastics. Okay. Another disadvantage of binary language and assembly language is that these languages are actually very architecture dependent. So very often what you would end up having is that a specific binary or assembly language would be bound to a specific processor or family of processors. So that if you write a certain program for using a specific assembly language, it can run on this family of processors, but it's totally useless to run on another kind of computer or processor or families of processors. What you want, obviously, is when somebody writes a certain program that you be able to run it on as many computers as possible. Portability, basically. So that's one of the goals that happened when in the early days of design of compilers. People wanted, because of course, when the first computers were designed and sold and made available, there was a quick succession of new computers coming out because the evolution of the technology was going very fast. And then there was literally every month or every year, there was a new computer that was totally different from the previous computer. So all the programs that you had written for this computer basically became obsolete and you had to rewrite them for the new computer. People wanted to have a system by which you could actually execute the same program on two different computers. So that you have retargetable, basically retargetable compilers or languages. So essentially eventually what you want is for a programming language to enable you to express higher level expressions such as this here. here this is a statement that basically says assign X to the value of the result of adding the value of Y and the value of Z, or the value contained in Y and the value contained in Z. So this notion of a variable is, yes, it's related to a certain value that is stored in a memory cell, but at least here you're not referring to this memory cell by address, or and here you're referring to add as a plus operation, which can be programmed in a more complex way rather than just being the add operation of the processor. Okay, so here basically this involves operations which are of higher level of abstraction. Of course, these needs to be translated into the lower level instructions. Okay, so that's what the compiler is doing. It's translating this here into, for example, assembly language like this here, which can then be translated into the machine language. Okay. So you see that assembly language very often, not always, but particularity of assembly language is very often there is a one-to-one relationship between an assembly instruction and an actual word that you put in the computer's memory. Whereas if you have one line of code in a higher level language, it most often is translated into a series of instructions. That's what makes higher level languages harder to actually translate, because one very small component of the language might be translated into a larger sequence of instructions for the computer to execute. Now, what was here I'm giving you an example of of one of the earlier languages. That's not the only one, it's just an example I chose. It's a very famous example, though, and it's a very representative example. So one of the first languages that was ever designed of higher level abstraction is Fortran. So of course, one of the things that people wanted to do with a computer earlier on is to compute numbers. For example, the army wanted to compute the trajectory of a missile that they may shoot into space to determine where it's going to land. Okay, that required a lot of computation, and initially that was done by people that would do the manual computation. That would require a very large amount of time to actually figure out all possible trajectories of, for example, a missile. So then came the computer, and then people in the army realized, well, we can use a computer to make all of these calculations. So then they quickly realized that we need a language to actually be able to do that, especially that considering that new computers were coming in, and then you had to rewrite the programs every time a new computer came out. So they said, we need some kind of language that is translated into the computer's operation. And that was essentially Fortran, or a formula translating system, formerly known as Fortran. This language, you might know it. Sure, some of you know that Fortran still is in existence, which is a very interesting aspect of the history of programming languages. There are quite a few languages that were some of the few first languages that are still in existence now, even actually used now. So that was designed in the 1950s. So that's one of the first examples of programming language. So many of the techniques that we know were invented in these early days. Even first Fortran compiler was invented before the parsing techniques were actually invented, which is a very interesting feat to be able to achieve that. So the Fortran language is a procedural language. It's also an imperative programming language. So there are lots of different kinds of programming languages, and I'm not going to discuss that in all details here. I suppose that you should have learned that in other courses, in 348, for example, COMP442. So it's a procedural language in the sense that a program is essentially a procedure that you follow to actually do some kind of computation. That would be as opposed to, for example, a functional language. In a functional language, you have some definitions, and these definitions are not to be executed in a sequence. They're just definitions that are out there, and they are using one another, not necessarily in a certain predefined sequence. Okay. Procedural programming language, you basically execute things in a sequence, in a procedure. And then you tend to create blocks of these, you could tend to create blocks of code that are a procedure that you may call as, for example, a function. Or procedural function as we know, which is different from a function in a functional programming language. A procedure is not exactly the same thing as it's actually quite far from the same thing as a mathematical notion of a function. I'm not going to go into all the details of this here. So all this to say that Fortran is a procedural language and it's an imperative language. Imperative language saying you're giving basically commands to a computer. So essentially a procedure is a series of commands that you execute in a certain order. Again, as opposed to a functional programming language where there's no commands, you're basically giving a certain definition and then you're asking for a certain value to be computed that is going to use the definitions in the program. We're not going to go and explain how to actually implement a compiler for a functional programming language in this course. We're going to see how to implement a compiler for imperative procedural programming languages. Not that it is entirely different. There's many things that are the same, concepts that are the same, but it is significantly different. Okay. So what Fortran was, what was the goal of Fortran was to provide a high-level programming language that enabled the scientists that were using the computer to actually write their mathematical formulas in the program and not having to somehow translate their mathematical formulas into the executable program. They wanted to write there as much as possible their mathematical formulas in the program, and then have a computer program that would translate these formulas into the executable version for these formulas. That was essentially the main idea behind Fortran. Of course, here, what they wanted to do is to use the power of the computer to save time. So, of course, a lot of emphasis was put in the efficiency of the code that was being generated so that the computer can be used as efficiently as possible. Okay. Yes, computers were running like thousands of times faster than a human can ever do the computations, but there was an enormous amount of computations to be done. And there was a lot of competition as to who's going to use the computer and so on. So the programs had to be very efficient in order to save as much time as possible. Also, their memory was somehow very reduced. So they had to use as less memory as possible to actually achieve a task. So the nature of Fortran is that it's very, very much concerned with efficiency, and it still is nowadays. So as Fortran was designed, it actually introduced some interesting notions that we take for granted now, but did not exist at the time. For example, the notion of comments, the notion that you could have inside of your program some explanations of what this program is doing. If you had to write your program in binary, all the code was to be executable code. There's no such code as explanations as to what the code is doing. So having a higher level programming language that is compiled enabled you to actually put inside of your file that is the program explanations as to what this program is doing, which of course made it much easier for other programmers to understand other people's code. Very important. Things like assignment statements, complex expressions, control structures, loops and conditional statements, subroutines and functions, which are part of the syntax of the language. Of course, in assembly language, you could have a subroutine, but you have to somehow hard code it. Okay, here the notion of a subroutine was syntactically present in the language itself, so that you don't have to hard code it. A lot of different things, for example, like arrays, where Fortran was one of the first language that used the notion of arrays, of course, which is a central aspect of computing. Okay, so Fortran and the early languages introduced many of the things that we take for granted now. There were other languages, such as Algol, that came a little bit later, that were much more languages that we, similar to those that we know now, but I'm not talking about them here. So how did people eventually, because let's put it this way, when people were designing Fortran, they were in uncharted territories. Okay? There was no such thing as parsing techniques and so on. So basically they started from scratch and then had to somehow figure out how to analyze the Fortran program and then how to actually translate it into an executable without knowing about parsing techniques or anything like that. Okay. So as they were doing this, they somehow invented some of the techniques that are, some of them are still used today, but the main techniques actually came from various places, as is often happening in computer science. Very often computer science is taking some ideas from apparently very remote fields. So in this case, for example, there was a linguist named Noam Chomsky, which you might know for being an activist, but he is main academic career was as a linguist. So what is a linguist? A linguist is basically a mathematician whose concern is about how to express languages in a mathematical form in order to be able to express languages, to reflect upon languages, and, for example, doing translation of languages. So Noam Chomsky was one of these linguists in the 1960s that were working on ways to formally represent human language. Using one of the things that he invented is the notion of a generative grammar. So a generative grammar is you have a list of rules that define your language, that define different building blocks of the elements of the language that you are using. And then essentially what you're doing is you're defining these rules, and then by applying these rules in a certain order, you can actually generate, for example, sentences in this language. That's why it's called a generative grammar. This notion of generative grammar is still used. It's almost the only thing that is used to actually build compilers nowadays. So you see that it basically, computer science is in this case using information or techniques that are designed in other fields. That happens very often in computer science. So this notion of generative grammar has been used ever since. So there's been a lot of, for example, parsing techniques that were invented based on the notion of a generative grammar. Okay. There were many parsing techniques that were designed in the 60s and early 70s. They are still used today. So there are some variations that are still invented today, but they're only slight variations or optimizations of the already existing techniques. So don't expect that you're going to have breakthrough new parsing techniques. So there was eventually, because you could have parsing techniques, which is a theory or an algorithm that you can use to somehow explain how you can use a generative grammar, the rules of a generative grammar to actually somehow parse a program to figure out if this program is valid according to the rules of this generative grammar. Basically saying you want to use the rules of the grammar and see if you can actually generate the sequence of tokens of this program. If you can, then that means that this grammar can generate this program. Thus, this program is valid according to the rules of the grammar. That's the essential idea. It's a formal proof that you are building. So you can actually build some kind of theory of algorithm that will be able to prove for any sequence of tokens if it is actually valid according to the rules of the grammar. That's what is a parsing method. So yes, you can design an algorithm such as this, but then what's much more interesting is that you would be able to have some kind of technique or program that would take a grammar and input and actually generate automatically a parser for this particular grammar. Okay. That's essentially saying you want to have a parser generator. That was the next step in the evolution of the design of compilers. So yes, you can use these parsing techniques and write a program that implements them for a particular grammar. It's much more interesting if you can have a program that would take the rules of the grammar and automatically generate a parser for it so that you don't have to write it by hand. In the course, as I want you to be able to know how to use the parsing techniques, I'm not going to allow that you use a parser generator. If you would be implementing a compiler in real life, you would for sure be using a parser generator, but because in this course I want also you to know how it really works from the inside out, you're not allowed to use compiler generation tools, or in this case, a parser generator. So there was a lot of different tools that were designed over the years, especially in the early years of compilers, to automate pieces of the compiler. Most notably, the parser. You might think, well, there's going to be new tools that are going to be totally automating the design of a compiler. That had not happened yet, and it's actually doubtful that it's going to happen ever. Well, it's maybe a bold statement, but let's put it this way. Automatically generating a parser is one thing, but automatically generate, for example, a semantic analyzer or code generator is a totally different magnitude of a problem. So, okay, so there's different ways you can actually do this translation. You have compilation, and you have interpretation. So essentially, compilation interpretation is or compiler and compiler is essentially two ways of translating a program. The question is, when is the program being translated? Okay. So what is a compiler? So a compiler essentially is translating the program directly in one single shot, more or less, translating your program into an executable in one shot before the program is actually executed. Okay. So the difference between compiler and interpreter is not about how the translation is done. The difference is not how the translation is done, it's rather when the translation is done. Okay. Compiler will, generally speaking, be translating the program before the execution of the program. Whereas, again, more or less, an interpreter is going to translate the program as the program is being executed. That's the main, again, roughly speaking, difference between compiler and interpreter. Nowadays, it's very actually common for the latest languages that we are now using to have some kind of hybrid model. For example, Java uses such a hybrid model. When you want to execute your Java program, you first have to compile your Java program into bytecode. So that's the compilation aspect of compilation part of executing your Java program. So there's a Java compiler, translate your Java program into bytecode. That's totally compiled. That happens before you execute the program. Then you take this bytecode, then you start this executable, which is your Java virtual machine. You put it on the computer's memory, and then you tell this program, execute this bytecode. And then the interpreter basically reads the lines of code that you have in your bytecode and then executes them as it goes. Okay, that's a general idea. So you see that you have compilation followed by interpretation. It's important to understand that whether you're doing compilation or interpretation, it's still translation. So that all the same steps of translation have to be done, whether you're doing compilation or interpretation or a mix of the two. Okay. There is kind of a family of languages nowadays that are called dynamic languages. The nature of these languages is that they tend, again, this is a rough description, they tend to actually leave much of the, or some of the analysis being done is left to be done during execution time. Why? Because it's more flexible. Okay. It has lots of severe disadvantages, but it also provides a lot of flexibility in the execution model of the programs. Okay, so what about specifically compilation? So compiler, what it is, it's a computer program, or in many cases, a set of programs. For example, if you're compiling your C++ code, as we shall see later as an example, there's actually quite a number of components involved in the compilation of a C++ program. So compiler is a computer program that transforms source code into an executable. Okay. So essentially here, your compiler is a program that you execute on your computer. It reads source code from a file generally, and then generates another file, which is an executable, which you can then load onto the computer and execute it. Okay. So its name compiler, name compiler is primarily used for programs that translate source code from higher level programming language to a lower level executable language. However, you can have a compiler such as the Java compiler that generates not executable, but generates another program, which you can then process further on, for example, by executing it on Java virtual machine. So that would still be called a compiler. Compiler is not necessarily about generating executable code. Now, what about interpretation? Interpreted language, well, that's a rather antiquated term, because it used to be, as I will mention later, that you would have, like in the early days of programming languages, you had families of programming languages. Some of them were interpreted languages, some of them were compiled languages. Okay. For example, you would have Lisp is an interpreted language, which is translated as you execute the program, whereas C is clearly a compiled language who is translated into an executable, and then you execute the totally translated executable at runtime. Okay. So it used to be you had interpreted languages and then compiled languages, and they were two totally different languages. Nowadays, there's no such clear distinction anymore. Okay. Nevertheless, if you want to talk about these in these terms, interpreted language It's a programming language. Those programs are not directly executed by the CPU, but rather executed by an interpreter. Okay, that's the main difference, and it's still nowadays how it is. If you want to rely on interpretation, your interpreter is actually a computer program that you must load onto the computer's memory and then feed it a program to execute. Here, this is actually what is the essence of one of the great disadvantages of interpretation. You need the interpreter that resides in the computer's memory to be there in order to execute the code. So this interpreter, for example, the Java interpreter, the Java virtual machine, is a very large program. So you need a very large program in order to execute your program, even if it's very small. Okay. So that's one of the disadvantages of interpretation. Yes, it allows you to have a lot of flexibility, like your bytecode program that you compiled, you can execute it on any other machine on which you can execute the JVM. But there's a cost attached to that, which is high memory consumption. Not going to go into all the details of this here, but I suppose that you would know about these things beforehand. Okay. Okay, well, one thing I said maybe interesting to know historically speaking, when you had interpreted language earlier on, in the early days, essentially you had your program, which is a list of, for example, statements or definitions, and then the interpreter, here I'm talking about the early days, the interpreter would take the code, like literally one line of code, would translate this line of code, generate some code, execute the code. Then we take the next line, translate the code, execute the code. So that, what happened is that if you had, for example, a loop that was executed 1,000,000 times, then every statement in this loop would be translated 1,000,000 times. Okay. Of course, that creates a terrible overhead because the translation cost is multiplied by the number of iterations. So that was very nice. It enabled you to execute the code, yes, but it made the code very slow to execute. The programming languages were identified as slow programming languages because of the mode of the execution. Okay. What is, of course, also what's happening here is that this analysis, for example, the translation, is happening at runtime. Whereas if you compile your program, then the analysis and the translation cost happens only once before you execute the program. That's why compilation is normally understood as being more, leading to more efficient execution rather than interpretation. And then there's, as I hinted at before, nowadays you have hybrid compilation and interpretation, whereby you may have source code, which is compiled and then translated into some kind of intermediate representation or intermediate program. For example, your Java code is translated into bytecode, which is stored in a file, which is a program that then needs to be executed using the interpreter, which is in this case the Java virtual machine. Let me move this. Okay. Okay, so then you basically take your compiled code and then you execute it on the interpreter. Okay. So here I'm giving the example of Java, but there is a lot of other languages like Python, Perl, Ruby. There's a lot of languages that are running on this model nowadays. So that's one of the things, yeah, that's just one thing I mentioned in the next slide, I believe. Okay. One of the things that's happening is that in the interpreter, you can actually have some kind of cache system that would remember what is the translation. For example, for your bytecode, the Java virtual machine would take some of your bytecode and then translate it and execute it. And then it would run some kind of cache that would remember that it actually had translated this particular line of code, so that if you execute this line of code again, that it would not have to translate it again. That's what is called, in case of Java, just-in-time compilation. So it essentially uses notion of the general notion of a cache to not have to translate too often the code that it had already executed before. Okay, so there's ways to actually make interpretation, in many cases, almost as fast as compilation. What's the advantage of having this compilation phase prior to the interpretation phase? So there is some part of the analysis that you may want to do at compilation time. One of the things is that if you have a purely interpreted language, then the analysis is all done at runtime. Now, what if you feed to your interpreter a program that is, for example, syntactically wrong? The interpreter would only figure out the error when it tries to execute this code that is syntactically wrong. So the only way that you would be able to know if your program is wrong is by executing it, which is kind of backwards and kind of dangerous. Okay, and then the only way you could actually foolproof or test or check the validity of your program is to actually test it before you actually put it into production. That's why if you use an interpreter model, very often it's very important that you have testing procedures that are very extensive if you want to have some kind of robustness at runtime. Also, it actually means that if you are doing a pre-processing phase, the compilation phase, then there is a part of the analysis that has been done once, and that would never have to be done. For example, your interpreter, your Java virtual machine, assumes that the bytecode that it uses is always valid code. There's no such thing as very heavy checking that is made on the bytecode as it is being interpreted, because the assumption is that it is valid. Okay, so basically you're saving time, analysis time, by having this pre-compilation phase that is doing a very important part of the analysis. So, and it also has a possibility to make your code more robust, the execution of your code more robust, by eliminating or filtering invalid programs or errors, or flagging errors at compile time before the program is executed. So which one is better? So I said most of the things about this at this point. So there's a debate about, is better to have compilation or interpretation? Well, this is also related to what's the nature of the language. For example, if you want to do compilation, one of the things that you assume you would be doing is doing some part of the analysis before you execute. Now that, for example, one of the things you might want to do is do type analysis. Now, if your language does not include types explicitly in the language, then it becomes very hard to do type analysis. Okay. So for example, when you write a C or C++ program, every variable that you define must have a type. Every function you define, their parameters must have a type. So there's types all over the place. It makes the language more cumbersome, but then it allows the compiler to very thoroughly check the typing of your program, so that as less as possible, there would be typing errors that happen at runtime. Okay. So whether or not you're doing compilation or interpretation, it also has to do with what is the nature, syntactic nature of the language. Okay. If you, in the language, you don't have types that are explicitly mentioned, yes, there is some typing that you can do, but you would have to do much of the typing at execution time as the language is being interpreted and executed. Okay. So it's not clear what is, you can't say clearly, for example, compilation is better. There's advantages to both, and it depends actually what you want to do with these programs. For example, if you want to have extremely robust executable, you should not rely on interpretation or a dynamic language. Okay? So you would be much more likely to rely on a very strongly typed, compiled language if your number one consideration is robustness of the program. So it essentially depends on what is your goal. Many things here I've already said, so I'm not going to repeat them. Now, here we go more specifically on the compilation process, or what are all the steps involved in the translation process. So let's take, for example, the example of a C++. So C++ is a compiled language, fully compiled language. There's no interpretation involved in C++, though there has been some C++ interpreters that have been designed. But the main way that people use C++ is by it being compiled. There's a lot of things that are happening when you actually compile your C++ program. So there's the preprocessor. So when you have hash include, any line that begins with hash is actually not C++ code. It's a preprocessor code. So a preprocessor is a separate component that takes effect before the translation is ever happening. So you see that you start having here different components that are interacting with one another in the translation process. Then if you have templates that you are using in your program, then you need to have a template processor or meta processor. Not going to go into all the details here. But if you're using templates, essentially the template processor is a code generator that reads certain templates and then generates C++ code, which is then translated, is then compiled. Yet another component that takes part in the whole compilation process. Then you may also have a library compiler, for example, a compiler that generates DLLs, which you can or not use in your compilation process. And then finally, as these different compilation units have been generated, possibly they are using one another, in which case you need a linker to actually resolve the linkage between your different compilation units. So yes, in real life, there is a lot of different components that are potentially interacting with one another. In this course, we'll concentrate on a standalone compiler that's doing the translation. We will not have linkage, preprocessor, templates. Of course, we will not have that, but that's an important aspect of most programming languages. So what are essentially the phases of compilation or the translation process? So these are the different phases. They are also very often separated into two blocks, being the front end and the back end. Some of you, I guess you know, some of you might know front end and back end, for example, in terms of, I don't know, web development, whereas front end is the rendering of the information. How do you design the part of the software in the browser so as to interact with the mechanics behind, which you call then the back end? That is not what we're talking about here. Okay. When you talk about front end and back end in a compiler, front end is about reading the source code and then generating some kind of intermediate representation that is not dependent on the target computer. Then the backend takes this intermediate representation and then translates it to a specific computer. So in compiler, front-end and backend has a totally different meaning. Front-end is computer independent and backend is computer dependent. That's one thing. There's many things here I will say that I'm going to say in the other slides, the following slides. So I'm going to fast forward on the following slides later. So essentially you have your source code here. And as you see, it goes basically as a pipeline. So it's a pipe. The compiler is very often mainly a pipeline architecture kind of system. So your source code, what is your source code? It's basically a file that contains characters. So you want to take this source code here. It is initially a sequence of characters. And what you want to do is eventually translate this sequence of characters into another sequence of characters, possibly a series of zeros and ones, which are then an executable you can load in the computer. But as we saw earlier, not necessarily. Maybe your output is, for example, bytecode. Okay. So essentially, you're translating a sequence of characters into another sequence of characters. That's essentially what you're doing. So source code comes in, it's a sequence of characters. First thing you need to do, you have a sequence of characters. What you want to do is analyze what's the meaning of the sequence of characters. Normally in the language, the building blocks, for example, are words. When I'm talking, I'm not giving a sequence of characters, I'm using words, which can be used. You can use, yes, letters to represent them, but essentially I'm using words. So lexical analysis, what it does is it transforms a sequence of characters into a sequence of words. So essentially, these are called tokens. Okay, so it translates a series of characters into a series of tokens, a sequence of words. Then you have your syntactical analysis, which is the parser, who is basically going to have inside of it the list of rules for this grammar of the language, and it's going to figure out if there's a possible way to translate this sequence of tokens or sequence of words into a valid program using the list of rules that are in the grammar that are embedded inside of this parser. So the parser is essentially some kind of a proof builder that tries to prove whether or not if the list of rules in the grammar can generate the sequence of tokens that is given an input. So it, yes, must do this proof. It must prove whether or not the sequence of tokens is valid, because if it's invalid, it cannot have a meaning anyway. Okay. That's one of the jobs that it's doing, but also as it's doing this, it may also want to translate this sequence of tokens into very often a tree that is representing the syntactical structure of the actual program. Okay. And the tree, as we will see later when we talk about parsing, the tree is essentially constructed by the notion that each of the syntactical construct of the language are represented by each a subtree of the whole tree. Okay, so now you transform your sequence of words into a tree. So here you transform a sequence into a tree. So you see that these are very theoretical kind of concepts. You have a sequence of characters, generate a sequence of words. Take a sequence of words, generate a tree. These are all things that you see in some of the theoretical courses or math courses that you saw before. Then what you want to do is to figure out if this program that you receive can actually have a meaning. Because, for example, I may utter some sentences which are syntactically correct, but are totally unintelligible. Okay. For example, sometimes when you read a poem, some poems would have some correct, syntactically correct sentences, but it's using imagery that makes it so that you have to think very hard to actually figure out what's the meaning of these sentences, because they may not appear to make some sense, but a human mind can actually find a sense to it. Here, of course, we're not talking about this. We're talking about a program, and it should be very clear what's the meaning of a program. And there should be very clear rules, semantic rules, to identify what is a semantically valid program. So that's what semantic analysis is going to do. For example, you're defining a certain variable, and then you're using this variable in conjunction with other variables. Are they all of the same type? Or when you call a function, you pass parameters to this function. Are you passing values of the correct types? These are all kind of syntax checking that you would do. Are you using an object? You're using a member of an object. Is this member a member according to the definition of the class, defining the type of this object? All these kind of things that we will actually do in the project. Then once you have this tree, which you might call an annotated tree, and which comes also with a symbol table that you'd be creating along the way, then you can actually do some optimization. So you have a tree, then you might actually analyze the tree and figure out, for example, there are two branches of the tree that are exactly the same. You may want to actually merge them together, or analyze the tree and realize that there's somehow a dead branch somewhere. So you may want to prune dead branches. So there's a lot of different kinds of optimization steps that may be done. This course is not gonna teach about optimization. Okay. You will not have to do optimization in the project. So here you would have basically this intermediate representation, which is the syntax tree, which has been optimized along with the symbol table. So all this here is not dependent on the computer. Whatever analysis you do or whatever you generate is not dependent on which computer you will run this program. Then what you have is a tree here and a symbol table. And then here what you want to do is to translate this tree into another program. So now you found a meaning, you've proven that this program is valid syntactically and semantically. Now you're going to basically translate this program into another program that is, for example, going to be an executable program. So that's why you need here to have target code generation. That's one thing that we will do in the project. And then you can, after you have the target code, then you can do a low-level optimization, which we will not cover in this course. So that's very fast forward kind of style here. This is what's happening in any compiler. Okay. So I already mentioned what is front end and back end. Front end, very quickly explained, front end is about the translation steps that do not involve in any way what is the target machine into which you're going to execute the code. And then its result is very often a tree along with a symbol table. Then this tree and this symbol table is given to the backend, which is then generating code, basically traversing the tree, using the information in the table to generate some code, which can then be optimized. So the backend is dependent on the target computer on which you are executing the code. So the phases here are going to some more details. Again, I've explained much of it in the preceding slide, so I'm going to skip some of the material here that I've already explained. So first is lexical analysis. So basically here translate a sequence of characters into a sequence of tokens. There is some theories and algorithms that have been designed which involve NDFAs and DFAs, deterministic finite state automaton or non-deterministics, and or actually both are being used in the theory. There is some lexical analyzer generators that exist based on this theory. We will cover this theory in the class, and then you will have to implement your own lexical analyzer. There are lexical analyzer generators you can use, but I'm not permitting you to use them in this course. Essentially, what a lexer or lexical analyzer generator is doing, it's taking a regular expression in input, it's transforming this regular expression into an NDFA, then it transforms it into a DFA, then implements this as a state transition table, which then generates, is combined with a predefined program that would basically read a sequence of characters and extract words according to the input regular expressions. Okay, so we will see this procedure in detail in the class, so you will have to implement it in the assignment number 1. So there's this notion of tokens and lexemes. For example, you might have keywords, which can be while, to, do, int, main. You can have identifiers that can be, depending on what's the definition of your regular expression that defines your identifiers. You can have identifiers like these ones here. So essentially, a keyword is an identifier that is part of a restricted set of words. And then you have tokens that are literal, such as numbers. So you can have, for example, the lexeme 123, which is character 123, can be a number literal that is a specific token. So you see the lexeme is actually the sequence of characters, whereas the token is some kind of category that encompasses many different lexemes that are according to the definition of the tokens in question, which is defined using a regular expression. Then you have syntactical analysis, which is done using a parsing method. So what it does, a parsing algorithm, what it does is it receives a sequence of tokens and it tries to figure out, the parser actually embeds somehow a list of rules in the grammar of this language, and it tries to build some kind of formal proof as to whether or not the rules in the grammar of the language can actually generate the sequence of tokens that is taken in input. Okay, so there is a wide variety of different parsing techniques. There's top-down techniques, bottom-up techniques. We'll cover many of them, not all of them in the course. I'm going to force you to use a top-down technique for the implementation of your compiler for reasons I will explain later on. Many, if not almost all, I might say, parsing techniques are using the notion of a context-free grammar. Okay. So I'm basically in assignment number 2, I'm going to give you a context-free grammar. I'm going to ask you to build a parser following this grammar. As we will quickly see, you will have to make transformations upon this grammar because I'm going to force you to use a top-down technique. There is some tools that you can use that you would use in real life if you want to build a parser, basically a parser generator that takes an input, the list of rules in the grammar, and then can generate automatically a parser. Okay. So we will see how this can be done in real life, and then you're going to be able to actually use this technique to build your own parser. So essentially the parser, what it does is that it receives this sequence of tokens like ID equal ID times ID semicolon. Then it has somehow embedded in the parser the list of rules. For example, very simplistically here, a statement is an ID equal E semicolon, and E or expression can be a multiplication expression, E times E, and an expression can also be an ID. So using these 3 rules, you can actually infer somehow that by using these rules here, you can build this tree that proves somehow that using these rules, you can generate this by, for example, traversing this tree here. You go ID is equal to ID times ID semicolon. Okay, so this, the parser would actually be making a proof using these rules in a certain order that can translate this sequence of tokens into this tree here, hereby building a proof that this sequence of tokens can be generated by the grammar that's embedded inside of the parser. Then following that, you have to do semantic analysis, because there can be, for example, some statements that are valid statements, syntactically valid statements that would be invalid. For example, if that would be, I don't know, in a Java program, it's possible, for example, that a rate would not have been declared before. Thus, you are using an undeclared ID. So that would mean that this statement is syntactically valid, but it's semantically invalid because rate is actually undefined or undeclared. So yes, you do syntax analysis and then semantic analysis. Not very often, but always semantic analysis involves a notion of a symbol table. So just quickly speaking here, a symbol table is essentially a dictionary that contains an entry for every of the things that are declared or need to be declared in the program. So for example, every of your variables that you are using here would need to have an entry in the dictionary. For example, storing what is the type of each of these variables, so that, for example, you can check if this statement is type correct. Okay. For example, can you multiply rate times time? And can you, if you can, then this results in a certain type. Can you assign this type to the type of distance? Okay. So that's what semantic analysis is doing. It would also check if you're calling a function, are you calling this function with the right number of parameters and type of parameters? Then you would have to, in order to determine the binding of the call to a function, to a specific function definition that you have in your program. Yep. So this is, normally this can be done as a separate procedure that follows the generation of the tree, but it can also all put together in a single process that is called a syntax-directed translation. We will see that later. So these different steps can be separate steps, but can also be merged into one, whereby as the analysis is done, the syntax analysis is done, the semantic analysis is also done, and then even the code generation is done as the program is being parsed. So if you want to do that, you would have to use syntax-directed translation. That's one of the things you will have to do. There is also, for semantic analysis, that's where it becomes more complicated. So there is such a thing as a syntax or parser generator that can take the rules of your grammar and generate a parser. There's no such thing that exists for a semantic analysis. What would need to happen is that you would need to have, instead of having a context-free grammar, you would need to have what is called an attribute grammar. Okay, so yes, that exists, but in the general case, it's not that much, how can I say, easy to generate a procedure, to create a program, to create a procedure that would automatically generate a semantic analyzer given an input attribute grammar. Okay, that's something that is theoretically possible, but there's a lot of, I would say, unknowns and variables inside of this procedure. There's no such thing yet as a automatic semantic analyzer generator. That's where it stops, basically, in the possibilities that we have now in automatically generating compilers. It actually stops somehow at the semantic analysis part. So essentially what you want to do is, let's say you have this in input, then your parser determines that this is the tree that corresponds to this statement. And what you want to do is your semantic analyzer would traverse this tree, determine if, for example, A has been defined before, Y has been defined before, if these operations are semantically compatible with these operands and so on and so forth. If you would be calling functions, it would check if the function is properly called and so on. And then eventually, as it does that, it would also generate the code that corresponds to what's the meaning of this program here into this other programming language that you want eventually to execute. Okay, so there's in syntactic analysis, there's two phases somehow. The semantic analysis that checks if the program is semantically valid. If it is valid, then you have semantic translation that actually does the translation part. Then once you have this, then you can actually optimize this. For example, you see here that T1 is equal to A, T2 is equal to Y. So essentially here, T1 is some kind of alias of A. T2 is an alias of Y. T4 is an alias of Z. So this is one thing, very simple thing that you can actually optimize. You can actually remove these here and then reduce the size of the code and number of instructions that are required to execute this code. So that's a very simple example of what you can do with a high-level optimization. If that's your output here, you can analyze this intermediate code and then somehow optimize the size of it or the number of instructions that it requires, or the amount of memory that it requires, or the number of registers that are required for it to execute, things like this. So there's a lot of different techniques that you can use to do optimization. Again, I repeat, we will not cover optimization in this course. Okay? Optimization is a very complex and large other topic. You could have an entire course on optimization techniques as part of compilation. So for example, if you, as I said, as I hinted at before, you could eliminate all the aliases here, and then you would end up having these 6 lines of code or instructions that would be translated or optimized into these 2 instructions or lines of code. Okay. So a lot of different techniques can be applied to optimize code, reduce the size of code essentially. Then the last part is code generation. So what you want to do there is to take this intermediate representation, which is not yet executable code, and then translate it into executable code. Okay. So essentially here you would have to have some kind of, you would be looking for some kind of pattern in a line. And then for each different kind of pattern, you would be generating another pattern that corresponds to the pattern you found there. Okay. It might appear here that I'm talking, but I'm saying that it should be pattern matching. Somehow it's what it is, but it's more kind of an exact pattern matching. It's not artificial intelligence here kind of patterns. Then once you have this code here, then there is low-level optimizations that can be applied. For example, you might want to execute this code on different processors, parallelize this code, execute it on different computers, or you might want to do other things like optimize the number of registers that are being used in the code, and so on and so forth. It's basically optimization that is dependent on the architecture on which you're executing the programs. Then there's a notion of these intermediate representations. How many of them do you have? Okay. So you could, normally what you have in most of the compilers, the compiler would actually along the way would generate a tree, as I explained before. So that would be your intermediate representation here. Okay. Intermediate representation here, so what I mean is it's a data structure that you use to represent your program. Whereas you can also have intermediate code, such as I had here. So that would be intermediate code, whereas a tree is an intermediate representation. So you can have either a intermediate code or intermediate representation. You can also have both. Why would you want to have both? Because an intermediate representation is more abstract, so you can have more high-level optimization, for example, by traversing the tree, analyzing the tree and see if there are common branches in the tree. There's a lot of optimization techniques that can be done on a tree data structure, for example, which is a high-level representation. Whereas intermediate code, you would need to analyze the meaning of the code and basically do some optimizations at code level, which is entirely different kind of optimization techniques that are involved here. In the project, we will basically, will ask you to build a tree, and then from the tree, you will generate the object code. So that's what we will do here in the project. So there is some, I would say, different components that are involved in the process. As I mentioned before, there's the symbol table. Symbol table is essentially some kind of dictionary that contains information about all the named entities that there are in the program that you are compiling. For example, if you define a class A, then in the dictionary, there would be an entry for A in a certain scope. So the symbol table is also, generally there's a symbol table for every scope. If there are subscopes, then there is a symbol table inside of another symbol table, and so on and so forth. So that's also what we will have to do in assignment number 3. Then you also have all the time, for all implementation of programming languages, you have what is called a runtime system. A runtime system is essentially facilities that are a group of not classes, but executable code that you need to have that are there to support the execution of your programs. For example, as you are calling, if you're using a procedural language and you're calling functions, in which there are some variables that are declared locally inside of your functions, then most often what you would have is some kind of stack mechanism. Now, if you're having a stack mechanism, then you may need to have some kind of meta mechanism that is there, is always loaded when you want to execute your programs. You have these facilities to manage the stack mechanism that is there to execute the programs. Okay. So runtime system is basically some predefined meta components that are there to support the execution of a particular program. Okay. In the course, in the project, we will have very, very primitive kind of a runtime system. So yes, there's going to be a stack, but you don't necessarily have to have a runtime system kind of thing that manages the stack. The stack can actually be hard-coded in the code that you generate, and that's what we will have. So we will not have a complex runtime system for the execution. Okay, so then I'm going to quickly go over that. So one of the things that is interesting is the history of, how do you generate the first compilers? As I mentioned before, it was very difficult for people to design the first Fortran compiler because essentially there was no compiler that was existing. So they had to write this compiler in assembly code or even machine code. Now, once they had this Fortran compiler, then they could actually use Fortran to design another compiler, either for a new version of Fortran or to design another language other than Fortran that you use Fortran to build a compiler for this other language. Okay. So that's how compilers are actually self-generating entities somehow. You can use a compiler to build another compiler. Once you have one compiler that can be used to write somehow any kind of program, you can use it to build other compilers. Okay. So that's how nowadays we can somehow very easily build new compilers because we already have compilers to build them. One of the interesting things also that is kind of a similar concept but different is that you can have cross compilers, in which case, for example, let's say in the early days of Windows, this is a hypothetical world here I'm describing. So let's say you have Linux, okay? You have Linux, you have your Linux C compiler. And here comes Windows, and nobody knows about Windows. Again, this is a hypothetical world here. So you have Linux, nobody knows about Windows. There's no compiler on Windows, but you have your Linux C compiler. So what you may want to do is to write your Windows C compiler in this language, basically Linux C. So this compiler here is a translator that translates, it's a code that implements a translator that translates the Windows C language into an executable that is runnable on Windows. Okay. So then you write this code here into Linux C, you compile it, and then that generates a compiler that is runnable on Linux that can actually generate Windows C code. Then what you do is you take this code again and you compile it using this compiler, and pop comes at the end of the pipeline your Windows C compiler that you can then take and execute on a Windows machine and then start using it. Okay, so that's what is called cross compilation. That's something that's very often done in real life. Here, this is of course a very simplified example. There's a lot of things that are happening in real life when you're developing compilers. I'm not claiming here that I'm going to teach you all the intricacies of what's happening in real life. I'm rather here to show you how a compiler works and how so that when you finish this course, you're going to understand what is a compiler and how it works. That's basically, yeah, for retargetable compilers. So let's say you want to, let's say you have, you have a compiler that generates code for a certain target machine. What if you want to have the same compiler for the same language, but that is targeting a different machine? So that's when it is actually would be beneficial to have a separation between the front end and the back end. So if you have a front end that generates the intermediate representation that is separate from the back end that generates code for machine one, then you can actually plug out the back end and replace it with a back end that generates code for machine two, then you would have a retargetable compiler. That's why it's very important to design your compilers modularly so that they are much more flexible, because there's new machines, new architectures that are starting to exist all the time. You want your compilers to be retargetable. Another very obvious thing is, for example, the Java model. When there's a new computer that comes in, what you need to do is not to redesign the entire Java compiler and interpreter. The only thing you need to do if a new computer comes out, you generate a new version of the virtual machine for this particular machine, and you make it runnable on this machine. And then you can take all your Java programs that are already existing and then feed them to this virtual machine, and boom, you can execute any program that was ever written in Java. So that's another way to make your executable your Java programs to be retargeted to a different new kind of machine. So that's it for that. I hope this was somehow comprehensive. Again, I'm not claiming here that I explained all the details. Some of you out there might be listening to my video and say, well, he skipped a lot of things. Yes, I had to cram that in somehow 1 hour. So that's hopefully that was useful in order to for the students to understand, have a general idea of what are all the steps involved and all the issues involved in the compilation process. Thank you.